Section 2.4, distribution shapes. We're gonna look at in statistics how we use shapes in statistics. So there are several shapes we're gonna look at. The distribution of a set data is basically a table, graph, or a format that provides the values of the observations and how often they occur. That's what we did in the previous section. We organized data in actually two sections, but we're going to focus only on the previous one for the quantitative data. We looked at how we find or construct the frequency table, relative frequency, and then from there how we get the graphs. Now after we graph this, we're going to look at the graph and see what kind of distribution does each graph has. So if we look at this talks about the height of females, like someone questioned them, and then from there they constructed the relative frequency and the histograms. So these histograms that we got here, they constructed kind of like a rough plot in black. As you see this curve is really smooth curve. We call it bell-shaped curve, and then it looks symmetric, like it's a symmetric shape. It looks symmetric. What we're gonna do with this is we are going to look at different shapes, not just this one. There's a lot more than this one to look at. And what do we need these shapes for, or what they help us with? For later sections, they will help us a lot in what we call to choose. It will help us to determine to choose the method of statistical analysis. We will see this in later chapters, but today we just get to introduce the different shapes that we have. First thing is, first part is called Unimodal here. Unimodal has one peak, as you can see, it's called Unimodal. If it has two peaks like that and they have to have the same height, that's called bimodal. If it's three or more, in this case we have 1, 2, and 3 or more is called multimodal. These shapes, we're going to be using the unimodal most of the time than the bi or multi. That's why we will focus on the unimodal from now on. But it's good to see the bi and the multi models as well. And then, so here just so this has one peak, that has two, that's 3 or more. They have the same height. The next shape, these are the important one, the first one, the bell shape, the one that I stated earlier. This is usually a symmetric one. We have the triangular and the uniform. The uniform is at the same level. The bell shape is the one that we use the most. This one is the one that we use the most. And notice, because it has one peak, both of them, those are called the unimodal from before, both of them. But the first one is the one that we use the most. For those shapes, we got two more shapes to introduce. One called right skewed and left skewed, or some people say skewed to the right, skewed to the left. That's when the tail on the right side is longer than the tail on the left side. And same thing with that one. Tail on the left side is longer than tail on the right side. That's what we called left. That's what we called right. So skewed to the right, skewed to the left. In statistics in general, it means more data falls on the right side. For the first one, for the skewed to the right, there will be more data if you plot it on the line. If you remember the dot plot, if you put more the plot on the line, most of the data will fall on the right side. If you do it on if most of the data falls on the left, that would be the skewed to the left. So let's say you have a dot plot like this, and then you put the data on the line on the dot plot like this, and then you notice that you have maybe something like that. And then if you try to trace it, it goes up and then down. You see like how the shape looks like? It's more toward the right side. So this is skewed right. Skewed left, it would be the opposite way. So this peak here shows you that majority of the data falls in that area. Same thing for this one. Majority of the data falls in here, in this region. So now, other plots or other thing very rarely used. This is a unimodal, and right skewed is called reverse G-shape distribution. Rarely used, but it's good to see it. If we look at this histogram, that's from the number of people. They were talking about the TV, maybe the TV, if you remember the example, or it could be any example. So after you plot the histogram or graph the histogram, then you can trace it. You can trace it. You can go up this way and down, and that's what was done in this figure. And you see that it's skewed to the right. It's not symmetrical. It's skewed to the right, more skewed to the right. So the idea here is you will be given a data. Data will be given. From the data, you're gonna construct histogram. Histogram or any chart you like a bar graph, histogram. Usually, as I said, we're doing for quantitative, so we deal with histograms rather than bar graphs. But let's say histograms, you can do like a dot plot. You can do stem and leaf plot. So stem and leaf or dot plot, and then from here, after we take the data, graph it or plot it, then we can look at the shape of the distribution. Shape of the distribution. And then that will help us, as I said, in statistical analysis later on. But now we're just learning what are the shapes of the distribution, what do we do, how do we get to that point, and then later we're going to see why we need to learn them. Now, what happens is if you have a population, if you remember from previous section, population means you have access to everything. You have access data about, let's say, a community. You go through the whole community and question each one in that community. That will take a lot of time. If you don't have access to the entire community, you're going to collect samples. So different people will collect different samples at different point, right? Different samples. And when we collect different samples and do run some studies, let's say someone goes to Woodbridge in Irvine, and then they start questioning people, random people. How many TVs do you have? And they collect this. A different person will go, same community but different houses. So they're gonna have to collect different data. So you will end up different people, different data. But then at the end, you wanna take all these different data, or called samples, you collect from the same population from that community, and then try to plot them on the graph. And here, what they did, they collected 6 samples. Notice these 6 samples, they questioned 100 people in that community. So this is the actual population. So if you access all the people and graph it, you get that one. But then different people collected different samples of size 100 and they plotted. That's the first sample, the second sample, third, fourth, fifth, and 6th samples. If you look at all these samples, those are meant to represent the entire population. Okay, and what you see in the first sample and the next one, next, all of them, they are roughly the same, right? Almost the same. So almost the same. Another thing, they look similar in shape. Do you see? They all look right skewed or skewed to the right. There's not like one skewed to the left, one skewed to the right, one symmetrical. And notice something about them. They all almost look the main one, the one in blue, the blue one. And that's another thing that is important for you to know. But what happens is they collected samples of 100. If in case we collect a sample of 200 or 300 or 500, the estimation here that we're getting is going to be, or the shape will be really more close to the actual population. In other words, as we increase the sample size, the distribution will get closer and closer to the actual population. In other words, the more we increase the sample size, the better the study we're going to have. And that's what is being mentioned here. For simple random sampling, the sample distribution approximates the population distribution. And then the larger the sample the size, the better the results, or the better the approximation tends to be. This is very important.